In PV2X, we set out to saturate your PV curiosity and answer questions like what PV technologies are being developed in industry and in research institutes, what are their fundamental working principles, their advantages and limitations, what elements do they use and how abundant are these elements, what engineering tricks are being used to create state-of-the-art devices and how efficient are those devices. And finally, how do we process these devices and measure them? In the next few videos, we would like to remind you of all the content covered in the PV2X Photovoltaic Technologies course. If some topics seem unfamiliar, we encourage you to return to the PV2X course and revisit those topics before attempting the practice or proctored exam. Let's go through the different PV technologies one by one. The dominant PV technology is based on the Group 4 semiconductor material, silicon. Crystalline silicon solar cells use boron and phosphor for the material doping. Nitrogen and oxygen are used for the chemical passivation layers, while aluminum is generally used for the electrodes. In this graph, the y-axis shows the number of atoms per silicon atoms in the Earth's crust. The x-axis shows the atomic number. The rock-forming elements, indicated by the green area, are most abundant and can most easily be mined. The precious and rare elements should generally be avoided as they are expensive and their availability can become an issue for upscaling. One of the reasons that crystalline silicon is dominant is that it only uses abundant, safe and relatively cheap materials. For electronic grade silicon, we need quartzite, which is a rock of almost pure silicon dioxide. Through a series of steps involving a 1900 degrees centigrade furnace and the addition of carbon-based compounds, the silicon is refined to 99% pure metallurgical silicon. To further purify the silicon, Chotralski casting or float zone pulling techniques can be used. The resulting electronic-grade silicon ingots can finally be cut to obtain silicon wafers used for photovoltaics. For a PV device to work, however, we need to separate generator charge carriers and transport them. To that end, dopants are added to the crystalline silicon to create the N or P doped wafers. On top of these doped wafers, an emitter layer is processed with an opposite dopant type. In week 2 of PV2X, we have discussed the design consideration for crystalline silicon solar cells. The open circuit voltage benefits from a higher emitter or back surface field dopant concentration, which will lower the contact resistance between the metal contact and the silicon. We have discussed an empirical relation between the open circuit voltage and the maximum obtained fill factor, but that in the reality, the fill factor is most affected by parasitic resistance. The front contacts of the cell contribute to the series resistance, and therefore the design of the front metallization grid is a trade-off between the emitter resistance, contact resistance and shading with LODOR JSC. To improve the short circuit current density, the front surface reflection can be reduced through texturing or an anti-reflective coating. Apart from these general design considerations, we looked at some advanced concepts for crystalline silicon solar cells. The PERC technology is now the most produced solar cell on multicrystalline silicon. We have also seen that the TOPCon design can replace the back surface field and localize contacts with an ultra-thin tunneling layer and full metallization at the back. The silicon heterojunction solar cell optimizes the open circuit voltage as the amorphous silicon passivation layers form a heterojunction with the crystalline silicon wafer. The metal wrap-through technology can be implemented for module optimization by transporting carriers collected at the front of the cell to the back. Using this design, the individual cells can be placed much closer to each other. The interdigitated back contacted design also places all the contacts at the back of the wafer and further increases light absorption by having no metallization at the front. In this design, all carriers are collected at the back. Finally, a combination of interdigitated back contact and the heterojunction yields the current record efficiency for a crystalline silicon cell. Then on to the thin film solar cells that are much thinner than the wafers used for crystalline silicon PV. As a result, much less material is used and most thin film technologies can be used for flexible applications. We will start with thin film silicon. Thin film silicon uses basically the same abundant elements as crystalline silicon. Unlike crystalline silicon, thin film silicon has an amorphous structure without any long-range order in the silicon network. Consequently, the defect density in amorphous networks is much higher and the charge carrier lifetime is much lower. Amorphous silicon solar cells are therefore not based on a p-n junction, but rather on a pin junction. This means that an intrinsic layer is sandwiched between the p-doped and n-doped layers. Between the p and n-doped layers, a built-in electric field is created across the intrinsic layer. Drift is therefore solely responsible for charge carrier transport in the absorber layer. As the p-doped and n-doped layers on these devices have a poor lateral conductivity, thin film silicon devices require a transparent conductive oxide or TCO to laterally transport charge carriers to the metal contacts. Thin film silicon devices can be grown in PIN or NIP sequence depending on the deposition order and in a superstrate or substrate configuration depending where the mechanical substrate is located with respect to the incident irradiance. An advantage of thin film silicon processing is that the bandgap energy of the absorber material can be tuned by varying the deposition condition. Here we see the AM1.5 spectral power density as it is observed on Earth's surface. Amorphous silicon has a bandgap energy ranging from 1.6 to 1.8 electron volt, depending on the hydrogen content. So that corresponds to this part of the spectrum, where all energies above the bandgap are absorbed and all energy below the bandgap are not absorbed. Nanocrystalline silicon has a bandgap energy ranging from that of silicon 1.12 electron volts to about 1.3 electron volt as it becomes more amorphous and hydrogenated. By adding germanium to the mix, the bandgap can be tuned from 1.4 to 1.6 electron volts. Adding oxygen and carbon can create amorphous silicon alloys with a bandgap energy of over 1.9 electron volt. This bandgap tuning allows for the processing of multi-junction solar cells which can reach higher efficiencies due to better spectral utilization. This concludes the first part of the PV2X summary video. In the next part we will continue with the chalcogenides.